So now I want to talk about how we would derive our heat diffusion equation using spherical coordinates. So I'm going to start off by drawing out our x, y, and z coordinates. So this is going to be x, y, and z. And we're going to choose some point here, and this point is going to be at a distance r from our origin. There's going to be some angle here we'll put as theta, and some angle down here we're going to put as phi. And our radii is going to extend some thickness that we are going to say is dr. And this is going to project down here. And our phi term is going to subtend outwards like this. This is going to make some change in phi here, d phi. And then these are going to project upwards and look something like this. And we can simply sweep our theta down like this. And we're going to make ourselves a control volume. And this is going into the page, so if you can kind of wrap your head around that. There's some change in angle here that we're going to say is d theta. And this length right across here is r sine theta. So our control volume has three components to it. It has r, theta, and phi. So we're going to start off by writing out an energy balance for this. So we're going to start off by figuring out what our differential volume is. Our differential volume is going to be this arc length, which is r d theta, multiplied by this arc length, r sine theta d phi, multiplied by dr. We can simplify this to look like r squared sine theta dr d theta d phi. And we can write out our term for energy storage. So the rate of change of energy storage, just like previously, is the density times the heat capacity times the change in temperature with respect to time, multiplied by our differential volume, r squared sine theta d theta d phi dr. Now we can start thinking about our net heat flows, and we're going to have those in three different directions. There's going to be radial and our angular. So we're going to start off by our net heat flow in our radial direction. And that is going to be the flow at some position r minus the flow at some later position r plus dr. So now we're going to use Taylor series approximations. So this is going to be QR minus the heat flow at some position r plus the derivative at that position r with respect to r times dr. Simplifying this, we'll find this is negative the derivative of the heat flow at r with respect to r times dr. And just as we did before, we can substitute in Fourier's law for this QR. So it's going to be negative the derivative with respect to r multiplied by negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to R times dr. And our area in the radial direction is going to be R squared sine theta d theta d phi. So this is R squared sine theta d theta d phi. So let's plug that in. We're going to have our negatives canceling. So this is going to be the derivative with respect to R multiplied by our thermal conductivity multiplied by R squared sine theta d theta d phi multiplied by the change in temperature with respect to R multiplied by dr. And we can take out these terms as those are not dependent on R. So this becomes the derivative with respect to R multiplied by the thermal conductivity times R squared, the derivative of the temperature with respect to R, times sine theta, d theta, d phi, and dr. So that is our net heat flow in our radial direction. So I'm going to point that out just because we're going to need that in a little bit. So now we can move on to our net heat flow in our theta direction, which just as before, it is the heat flow at some point theta minus the heat flowing at some later point theta plus d theta. Again, we're going to use Taylor series approximations, so this becomes q theta minus q theta plus the derivative of q theta with respect to theta times d theta. Our q thetas cancel, so we're going to be left with negative the derivative of q theta with respect to theta times d theta. Once again, we're going to plug in Fourier's law. So this is going to be negative the derivative with respect to theta multiplied by our negative thermal conductivity times the area times the change in temperature with respect to theta times d theta. And you'll notice that we have these derivatives with respect to a position, not an angular change. So we're going to have to change this to be an r d theta. So we're going to simplify this to have an area that is r sine theta d phi dr. So plugging this in, our negatives cancel. We're going to have the derivative with respect to theta multiplied by our thermal conductivity multiplied by r sine theta d phi dr times the derivative of the temperature with respect to theta times r d theta. So we'll see our r terms cancel. And we can take out this d phi and dr, but our sine theta must stay in there. So this is going to be the derivative with respect to theta times the thermal conductivity multiplied by sine theta, the derivative of the temperature with respect to theta, multiplied by d theta, dr, and d phi. Now we're going to move on to lastly our phi. So this is going to be the net heat flow at phi, which is equal to the heat flow at some phi minus the heat flow at some later phi plus d phi. We're going to use Taylor series approximations for this, so this is going to be q phi minus q phi plus the derivative of the heat flow at phi with respect to phi d phi. Our q phi's cancel out, and we're going to be left with negative the derivative of q at some phi with respect to phi multiplied by d phi. Now we're going to plug in our Fourier's law. So this is going to be negative the derivative with respect to phi multiplied by negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to phi times d phi. And again, this is with respect to an angle and not a position. So we're going to have to change this to be negative d over d phi times negative k a, the derivative of the temperature with respect to r sine theta d phi, in order to make that units of position, times d phi. Our area for this is going to be r d theta dr. So simplifying this, our negatives cancel. We're left with the derivative with respect to phi multiplied by k times r d theta dr, the derivative of the temperature with respect to phi multiplied by r sine theta times d phi. Our r terms are going to cancel. We can take out d theta dr as well as sine theta, so this becomes the derivative with respect to phi multiplied by k times the derivative with respect to phi multiplied by 1 over sine theta d theta dr d phi. Now we can simply combine all of our net heat flow terms. So we're going to have our energy storage term first, which we said was the density times the heat capacity times the change in temperature with respect to time, multiplied by our differential volume, which was r squared sine theta d phi dr. This is equal to the sum of our net heat flows. So that was this term right here in our radial direction, plus the net heat flow in our theta direction, plus our net heat flow in our phi direction, and finally, we can't forget about our energy generation term, which is Q dot times our differential volume, which is r squared sine theta d phi and dr. Now, once again, just as before, we want to isolate our temperature per time, so we're going to divide by our differential volume. So when we do that, we're going to have a leftover 1 over r squared over here. So we're going to put 1 over r squared here. Right here, we're going to have a 1 over sine out here, 1 over sine theta, and a 1 over r squared over here as well. And here this becomes a 1 over sine divided by sine, so this is going to be sine squared theta, and we can't forget about this 1 over r squared, and that term fully cancels. You can also see that we're left with this rho c term. If we assume that our thermal conductivity K is constant in all of these cases, we can take it out of our derivative, and that way we can divide by rho c and get our alpha term. So this is all going to simplify to the derivative of temperature with respect to time is equal to 1 over alpha times 1 over r squared d over dr multiplied by r squared dt over dr plus 1 over r squared sine theta, the derivative with respect to theta, multiplied by sine theta, the derivative of the temperature with respect to theta. And lastly, we're going to add our energy generation term and divide that by rho and c. And that is how you derive the heat diffusion equation using spherical coordinates. Okay, so now I want to take an example of steady state with no energy generation and heat only flowing in the radial direction with our heat diffusion equation for spherical coordinates. So if we simplify all of that, we're going to be left with r squared multiplied by the derivative of temperature with respect to our radius is equal to a constant. We'll just say C1. This is a separable differential equation, so we can separate our terms to be dt is equal to C1 over r squared dr. Now we can integrate, and we are going to integrate from T1 to T2 and R1 to R2. Over on the left, we're going to be left with a delta T, and this is going to be equal to our constant C1 multiplied by 1 over R1 minus 1 over R2. Now we can solve for C1. C1 is going to be equal to our change in temperature divided by 1 over R1 minus 1 over R2. And once again, this is going to be analogous to our electrical circuits where we had our Ohm's law that was the change in voltage is equal to our current multiplied by our resistance. We can say that the change in temperature, our driving force, is equal to our heat flow Q multiplied by a thermal resistance. We know that Q can be found using Fourier's law, which is negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to our radius. And we can evaluate this at either one of our radius if we choose 1 or 2. For the sake of this, I'm going to choose 2. So I'm going to say R is equal to R1. Therefore, our area is going to be 4 pi R1 squared. And our dt over dr can be found up here. If we say that dt over dr is equal to C1 over r squared. And again, we were evaluating at R1, so this is going to be R1 squared. So we can substitute this in. We're going to have Q is equal to negative K times 4 pi R1 squared multiplied by C1 over R1 squared. Our R1 squared terms cancel, and we're left with Q is equal to negative our thermal conductivity multiplied by 4 pi multiplied by C1. We already established up here what our C1 is, so we can plug that in. So our heat flow Q is equal to negative K, our thermal conductivity, multiplied by 4 pi, multiplied by a change in temperature delta T divided by 1 over R1 minus 1 over R2. And we can rearrange this to look like this. So we're going to have delta T is equal to Q multiplied by 1 over R1 minus 1 over R2 divided by negative 4 pi K. And as you can see just by looking at this, that our thermal resistance term for spherical geometry is going to be this expression right here.